Hello, everyone. Welcome. Hi, I'm Oliver.
Hi, I'm Lily.
Welcome to Science in Easy English. How do dolphins sleep without drowning?
It's um it's a completely wild question when you really sit down and think about it.
Right. I mean, imagine being physically unable to stop swimming for like 2 solid months.
Yeah.
If you stop moving, you sink. And if you sink, well, you drown.
Yeah, and on top of that, every single breath you take is a conscious decision.
Exactly. You never get to just put your body on autopilot. Now, how in the world are you supposed to get any sleep?
It sounds like an impossible biological riddle, honestly, but marine mammals have completely solved it. So our mission for this deep dive is to really unpack the extreme biological hacks that allow these animals to, survive, rest, and thrive in this incredibly unforgiving ocean environment.
And we're looking at a fascinating stack of sources today to do just that.
Oh, absolutely. We're pulling from recent genetic studies in PLOS genetics, some really intense behavioral research on dolphin mothers and their calves, and some cutting-edge neuroscience out of UC Berkeley.
Awesome. So let's start by thinking about the fundamental difference in how we operate compared to, say, a whale or a dolphin. For you and me, breathing is entirely involuntary.
Right, you don't even think about it.
Exactly. You are listening to this right now, taking breath after breath, and you haven't had to consciously command your diaphragm to contract even once. But for cetaceans, breathing is voluntary.
Every single trip to the surface, every time they open that blowhole, it requires a conscious command from the brain.
Which creates this ultimate evolutionary bottleneck.
It really does. I mean,
Yeah.
if a dolphin were to lose consciousness entirely, falling into the kind of deep bilateral sleep that you or I experience, it wouldn't just automatically keep breathing.
It would suffocate.
Yeah, it would just stop breathing entirely.
But they still need the brain-restoring benefits of sleep, right?
Right.
Nothing with a complex nervous system can survive without it. But surrendering to sleep means death. So how do they bridge that gap?
Well, they split the difference, literally. The evolutionary workaround is this thing called unihemispheric slow-wave sleep, or USWS.
USWS. Okay.
Dolphins sleep with only one half of their brain at a time. The other half stays completely awake and online.
Okay, let's unpack this because picturing an animal functioning on a split brain schedule is wild. If we were to hook a dolphin up to an EEG to monitor its brain waves during this state, what does that actually look like on the monitors?
You would see a perfect real-time split screen of two totally different states of consciousness. I mean, one hemisphere of the brain would be broadcasting the high-amplitude, low-frequency waves, which that's the classic biological signature of deep restorative sleep.
Right, the deep sleep waves.
Exactly. But then the monitor tracking the other hemisphere would be displaying the fast, low-amplitude waves of complete hyper-alert wakefulness.
A brain divided. That is crazy. And you can actually observe the physical reality of this if you watch them closely, because their optic nerves cross over, right?
Yes. The eye opposite the sleeping hemisphere actually closes, shutting out visual input to give that resting side a break.
Meanwhile, the eye opposite the awake hemisphere stays wide open, just scanning the environment.
It's amazing. And back in the 1960s, a researcher named John Lilly actually predicted this behavior. He realized that because their breathing was voluntary, they just couldn't afford a full system shutdown.
So he hypothesized they might sleep with one eye open to watch for predators.
Exactly. And it actually took years before EEG studies conducted by a Russian researcher named Mukhametov finally provided the hard data to prove this, asymmetrical brain state was actually happening.
Wow. You will sometimes see dolphins engaging in a behavior called logging, where they just float motionlessly at the surface, kind of looking like a piece of driftwood with one eye closed.
Right. But they also maintain this unihemispheric sleep while actively swimming.
And this is where I get hung up. Because if I try to do anything requiring cognitive effort after a terrible night's sleep, I'm completely useless. My brain fog is thick. I make mistakes.
We've all been there.
Right. So if a dolphin is actively swimming, navigating, and coming up for air while literally operating on half a brain, their awareness and cognitive performance must take a massive hit, right?
What's fascinating here is that the data shows the exact opposite.
Wait, really?
Yeah, their cognitive performance doesn't drop at all. To really understand the sheer horsepower of a dolphin's brain under these conditions, we have to look at a behavioral study conducted by researcher Brian Branstetter.
Okay, what did this team do?
They wanted to test exactly how effective this half-brain sleep actually is, so they focused on echolocation.
Which requires immense processing power. I mean, they are sending out rapid-fire clicks, waiting for the sound waves to bounce off objects in their environment, and then computing those returning echoes to map their surroundings in real time.
It's super complex. So Branstetter's team set up an environment to test 2 dolphins, requiring them to continuously echolocate and report the presence of specific random targets.
And they wanted to see how long these animals could keep this up without their performance degrading.
Exactly. And the result was a continuous, uninterrupted marathon of 15 straight days.
Think about that for a second. 15 days of uninterrupted, complex mental math.
It's mind-blowing.
I mean, if a human stays awake for even 48 hours, they start experiencing microsleeps and severe cognitive decline.
Well, the dolphins maintain near-perfect accuracy. One of the subjects was hitting up to 99% accuracy at identifying targets across the entire 2-week period.
99%.
Yeah.
While sleeping with half a brain.
Yeah. They were seamlessly swapping which hemisphere of their brain was asleep, all while continuously pinging their environment, analyzing the acoustic feedback, and accurately identifying targets without a single break.
But did the researchers see any physiological toll? Because even if I manage to power through a few days of exhaustion, my body is flooded with cortisol. I feel physically wrecked.
That's the craziest part. Blood tests taken during the study showed absolutely zero physical signs of sleep deprivation.
None.
None. No stress hormone spikes, no exhaustion markers, nothing. They were operating at peak physiological efficiency the entire time.
That kind of vigilance is incredible, but it demands the question why. Evolution doesn't build a 15-day half-brain radar system unless the environment absolutely demands it.
Right. It is entirely about survival in a highly dangerous ecosystem. Dolphins often live in murky coastal waters where visibility is just terrible, and they're under constant threat from shark predation.
Ah, right. The sharks.
Yeah, in one specific study region in Western Australia, researchers observed that nearly 3/4, 74% of the non-calf bottlenose dolphins had visible shark bite scars.
74%. That is brutal.
In an environment like that, losing situational awareness for even a few minutes can be fatal. Interestingly, this environmental pressure has produced similar half-brain sleep adaptations in completely different species, too.
Oh, really? Like what?
We see a mirror of this strategy in certain birds, like flocks of mallards.
Wait, so birds are splitting their sleep too?
They are. When a flock of mallards settles down to rest, they exhibit something called the group edge effect.
Group edge effect. How does that work?
The ducks that are lucky enough to be sleeping in the center of the flock, they'll shut both eyes and sleep fully. But the ducks on the outer perimeter, the edge of the group, they'll use unihemispheric sleep. They keep their open eye facing outward, acting as sentinels, scanning for terrestrial predators.
Wow, they form a living security perimeter. But does a dolphin pod organize itself the same way? Are they always keeping that open eye pointed out into the murky water to watch for sharks?
Actually, in some species, like Pacific white-sided dolphins, researchers have observed the exact opposite. The open eye often faces inward, directly toward the rest of the pod.
Wait, so they're turning their back on the potential threat just to watch each other?
Exactly. It reveals that unihemispheric sleep serves a dual purpose. It's not just an anti-predator alarm system, it's a critical tool for social cohesion.
That makes sense. The ocean is vast and dynamic with strong currents and low visibility.
Right. They need to maintain a visual lock on their pod members to ensure they don't get separated while they rest.
You know, that idea of social cohesion leads us perfectly into the most intense, high-stakes relationship in the ocean. A mother dolphin and her newborn calf.
Oh, definitely.
If we are talking about the necessity of constant movement and constant vigilance, nothing compares to the vulnerable period right after birth.
It is one of the most extreme biological gauntlets in the animal kingdom.
Here's where it gets really interesting. We have a behavioral study here looking specifically at bottlenose dolphin mothers and their newborns. For the first 1 to 2 months of a calf's life, neither the mother nor the calf stop swimming.
Not even for a minute.
Nope. They don't log at the surface. They don't rest on the ocean floor. They engage in something called echelon swimming, almost entirely nonstop, day and night.
And echelon swimming is basically a masterclass in hydrodynamics. The mother swims, creating a slipstream or wake behind her, and the calf tucks itself right into that specific zone, effectively getting pulled along by the water pressure generated by the mother's movement.
The sheer mechanics of why they have to do this are brutal, though. When a dolphin calf is born, it doesn't have a developed layer of blubber yet.
And blubber isn't just for insulation, it's their primary source of buoyancy.
Exactly. So if a newborn calf stops swimming, it literally sinks like a stone.
They are trapped in a state of perpetual forward momentum.
And while they are locked in this 2-month marathon, that open eye we were talking about earlier, it's directed right at the mother nearly the entire time. They are obsessively, continuously monitoring each other's position to maintain that exact hydrodynamic slipstream, all while swapping their sleeping brain hemispheres back and forth.
It's exhausting just thinking about it.
But I have to push back on the thermodynamics of this. The ocean acts as a giant heat sink, constantly pulling warmth away from the body. If a calf with no blubber is swimming continuously for 2 months, burning massive amounts of caloric energy, how do they not freeze to death? And chemically, how does the brain tolerate the total absence of deep, motionless rest?
To understand how they survive the cold and the endless motion, we really have to look at how their neurochemistry wildly diverges from terrestrial mammals. First, cetaceans have completely eliminated a specific stage of the sleep cycle. They do not experience REM sleep.
Wait, no REM sleep, which is the stage where humans typically dream, but it also comes with a major physiological side effect, right?
Yeah, in land mammals, entering REM sleep triggers muscle atonia, essentially, temporary paralysis of your voluntary muscles. It's a safety mechanism so you don't physically act out your dreams and injure yourself.
Right, that makes sense.
But think about what muscle atonia would mean for a marine mammal.
Oh, wow. If a dolphin goes into paralysis, the forward momentum stops, they sink, they stop breathing, and they drown.
Precisely. Evolution essentially ripped the emergency brake out of the vehicle. By completely scrapping REM sleep, a dolphin never experiences that paralytic state. And this ties directly into your question about freezing.
How so?
Because they never enter REM, a highly specialized area deep in their brainstem called the locus coeruleus is continuously firing.
The locus coeruleus. What exactly does that do when it's firing?
It's essentially a chemical engine that releases a neurotransmitter called noradrenaline. In humans, when we hit REM sleep, this area shuts down, stopping the flow of noradrenaline. But in dolphins, this continuous release maintains a constant level of basal muscle tone.
So their muscles are always slightly engaged.
Yes, always humming. And that constant low-level muscle tension generates a continuous internal furnace of heat. It's a physiological process called thermogenesis.
Wow. So the act of skipping that paralytic sleep stage is what keeps their internal engine running hot enough to survive the cold water, even for a vulnerable calf.
Exactly. And the brain acts as a highly efficient thermal manager. Measurements show that the actual temperature of the brain drops slightly in the sleeping hemisphere, conserving vital energy, while the awake hemisphere stays warm and functional.
That's incredibly efficient.
It really is. And if we connect this to the bigger picture to see how deeply integrated this is, we have to look at some incredible neuroscience research from UC Berkeley involving mice.
Right. The Berkeley researchers were looking at the mechanical relationship between different stages of sleep and brain chemistry.
Yeah, they mapped out this fascinating biological feedback loop. They discovered that when an animal enters deep, non-REM sleep, the brain triggers the release of growth hormone.
And that growth hormone doesn't just repair the body, right?
No, it actually travels back into the brain and activates that exact same area we just discussed, the locus coeruleus. The growth hormone acts as a trigger to regulate wakefulness, alertness, and cognitive focus for the next cycle.
So the chemical produced during deep sleep, is the very key required to unlock the brain's wakefulness center.
Yes. Now imagine the sheer complexity of applying that feedback loop to a dolphin's split brain.
Oh, wow.
This intricate chemical dance between deep sleep, the release of growth hormone, and the arousal of the locus coeruleus has to be flawlessly isolated within each individual hemisphere.
Because they're sleeping one half at a time?
Exactly. While one half of the brain is sinking into deep sleep and producing the hormones, the other half is actively utilizing those chemicals to stay incredibly alert and keep the animal swimming.
It's like having two completely independent electrical grids powering the left and right sides of your house, and a master computer has to perfectly route the voltage so the lights never go out.
That's a great way to put it. And they're managing other neurotransmitters on this tightrope as well. Acetylcholine, which is crucial for learning and attention, is heavily lateralized in the dolphin brain.
Meaning it's separated by hemisphere.
Right. The brain pumps it into the awake hemisphere at maximum levels to maintain that razor-sharp focus we saw in the 15-day echolocation study. Meanwhile, it drops the acetylcholine levels to an absolute minimum in the sleeping hemisphere. It is a chemical juggling act occurring every second of their lives.
So what does this all mean? We've established the mechanisms. We know they sleep with half a brain. We know they avoid drowning and freezing by scrapping REM sleep and riding a continuous wave of noradrenaline and acetylcholine.
Yeah.
But taking a step back, dolphins evolved from terrestrial land mammals. Millions of years ago, their ancestors walked on land and likely experienced the same 24-hour full shutdown sleep cycle that we do. How do they rewrite their own neurochemistry to survive the return to the ocean?
The answer lies deep in their DNA, and a breakthrough study published in PLOS Genetics finally gives us the blueprint. Researchers wanted to find the genetic root of this ability, so they analyzed 8 canonical circadian clock genes across a wide variety of mammalian species.
The circadian clock genes being the core biological programming that dictates when our bodies feel tired and when we feel awake.
Exactly. And the researchers found massive evidence of positive selection, meaning highly beneficial evolutionary mutations specifically within these clock genes.
But they only found these distinct mutations in marine mammals that utilize unihemispheric sleep.
Yes, this is a classic case of convergent evolution. Different species of whales and dolphins facing the same intense environmental pressures of the ocean independently arrived at the same genetic solution.
But finding the mutated genes on a computer screen is one thing. The researchers took this a massive step further to prove what those specific mutations actually do inside a living organism, didn't they? And they did it using zebrafish.
They did. Zebrafish are incredibly useful in sleep research. Under normal circumstances, they have very predictable diurnal sleep patterns. They are active during the day, and they shut down and sleep at night, very much like we do.
So the scientists isolated the cetacean-specific mutations, focusing on 2 core clock genes known as CLOCK and BML1 or BML2, and then they used genetic engineering to insert those specific whale mutations directly into the DNA of the zebrafish.
They essentially swapped out the fish's default biological timing chip and installed the cetacean version. And the results were immediate and stark. The mutations fundamentally rewired the neurochemistry of the zebrafish brain.
How did it change it?
To understand how, think of the brain's chemical pathways like a massive audio mixing board. The cetacean genes grab the faders for the glutamatergic pathways and push them all the way up.
And glutamate acts as the brain's primary excitatory neurotransmitter, right? So pushing those faders up means flooding the brain with signals that promote intense wakefulness and activity.
Simultaneously, the mutated genes grabbed the faders for the GABAergic and cholinergic pathways and pulled them way down. GABA is a major inhibitory neurotransmitter. Its job is to slow down brain activity and promote relaxation and sleep.
So the genetic code literally turns up the volume on the pathways that scream, stay awake, and mutes the pathways that whisper, go to sleep.
Exactly. And the behavioral change in the genetically modified zebrafish was exactly what you would expect. The fish with the whale gene slept significantly less than normal zebrafish.
Did they keep swimming?
Oh yeah, their locomotor activity skyrocketed. They were in a state of near constant movement, mirroring the endless swimming of a dolphin pod.
It is absolutely staggering to realize that tweaking just a few lines of code in those core circadian clock genes allowed the terrestrial ancestors of whales and dolphins to completely break free from the universal mammalian need to shut down for 8 hours a day. It was the genetic skeleton key that allowed them to conquer the oceans.
It really is one of the most elegant and extreme adaptations in evolutionary history.
So for everyone listening, take a moment to absorb the sheer scale of the biological engineering we've explored today. We started with the seemingly impossible problem of how an animal that must consciously choose to breathe can ever afford to sleep.
Right.
We've seen how they physically split their consciousness in half, maintaining such a high level of cognitive processing that they can track sonar targets for 15 days straight without a hint of biological stress.
And we uncovered how this split brain adaptation is the ultimate tool for social cohesion, allowing newborn calves to survive a brutal 2-month marathon of continuous swimming by relying on an internal furnace powered by a brainstem that never stops firing.
And we traced it all the way down to the fundamental source code, seeing how a handful of genetic mutations in a biological clock rewired an entire neurochemical system. The next time you wake up feeling groggy, heavily caffeinating yourself just to get through a morning meeting, take a deep breath and just be incredibly thankful that your brain handles the breathing for you while you are unconscious.
I want to leave you with a final thought to mull over. We've seen how cetaceans evolved these specific genetic mutations to completely bypass the need for bilateral sleep and the paralytic dangers of REM. As humans look toward our own extreme frontiers, whether that's deep space travel where resources are incredibly limited, or colonizing harsh, unforgiving environments, could we eventually look to the ocean for our own biological upgrades?
Oh, wow.
Could advanced gene therapy be used to mimic these exact circadian mutations in astronauts? Unlocking the dolphin's genetic sleep switch might eventually be the key to engineering a human being capable of functioning perfectly while only ever sleeping with half their brain at a time.
Now that is a thought that will keep you awake. Thank you so much for joining us for this deep dive. We hope you walk away seeing the ocean and your own nightly sleep schedule with a completely new appreciation. Until next time.